All right, I think we're just about ready to get started. So, hi everyone, welcome to the monthly seminar of the IAU Working Group on Active B-Stars. This month's seminar is going to be given to us by Dr. Yanina Cochetti from the Instituto de Astrofísica de La Plata in Argentina. Dr. Cochetti did her PhD at Universidad de La Plata, and is also currently involved in the POEMS program with Dr. Michele Kraus. So with all that being said, Dr. Cochetti, please take it away.
Hi, Alex. Thank you for introducing me and thank you for the invitation. Well, I will talk about infrared spectroscopy of BE stars. This is like the general schedule for this talk. I will give a brief introduction on BE stars. I will talk about the infrared atlas and the observation that we made in the infrared spectral region. I will talk about the analysis that we made on synthetic spectra and why we found interesting to work with synthetic spectra, and our next steps in the following. So in case you are not familiarized with BE stars are usually B-type stars that present or have presented in some moment hydrogen emission lines, especially H-alpha. And this emission came from a circumstellar envelope that surrounds the star, which are mostly compatible with a disk geometry in Keplerian rotation. Here it is an schematic image for the BE star. This is the central star and the disk that surround it. And you can see here different lines that we can observe, like H-alpha, H-beta, or some helium lines, iron lines that you can see in the spectra. And depending on how we are observing this star, the shape of the line profiles will be different. If we observe in a polon orientation, we can see that, for example, H-alpha has only one peak. But if you see from the equator, you can see two profiles or even a spectra that we call shell-type spectra. In the infrared region, these stars present a moderate flux excess and numerous H lines that came from the envelope. And these lines are formed in a region that is closer to the star than those lines that we can observe in the optical spectral range. Also, the photospheric absorption of these lines is almost negligible. So these things makes the infrared emission lines a great tool to obtain information about the physical structure and dynamics in the innermost part of the disk than if we observe in the optical spectral range. Fortunately, this spectral range has gained importance in the last decades, and it's becoming to be more important in the analysis of the BE stars. So I will mention a few works that I found interesting and that my work used part of these results. So one of the first works that I would like to mention is the two works by Lenorser and collaborators from 2002. The first one was an atlas with L-band observations of different kind of early stars, not only classical B, regular B star, but to BE, B bracket D, and LBB objects. So you can see here a spectra that they publish. Here is a spectra of a BE star, a B bracket star, and an LBB star in the L-band. You can see here bracket alpha line, bracket gamma, the Fund series, Humphrey series, Fund delta. So they made a diagram based on the line flux ratio of some lines. Here you can see that they use Humphrey 14, that it's the line that it's here, and Fund gamma, that it's the line here, and Humphrey 14 and bracket alpha, that is the line that I showed you before here. So they put the line flux ratio in this diagram, and they put also the optically thick limit, the radio that we expect if the envelope is optically thick, and the position if the envelope is optically thin. So they found that BE stars are in this position in the diagram, that in the middle are the BE bracket star, and that in this region, more close to the optically thin case, are the LBB position in this diagram. So they say that, well, the line strengths of the lines are sensitive, and it can give us information about the density of the emitting gas. After that, Meniken and collaborators observed a sample of BE stars, and they classified according to how the L band of the stars are. BE stars into 3 different groups. Here you can see the L band spectra for the stars that they classify as in group 1. That the main characteristic is that Humphrey lines are as intense as Fun gamma and bracket alpha. You can see bracket alpha. Here is the line more in the righter part of the spectra. Fun gamma is one of these 2 lines together, and Humphrey lines are all the others. So if they present similar intensities, you classify the star as in group 1. In group 2, they put the stars where the Humphrey line series are not as intense as bracket alpha and Fun gamma. You can see here, or these smaller lines are the Humphrey series, and the more intense are bracket alpha and Fun gamma. So if Humphrey are not as intense as bracket alpha and Fun gamma, the star is classified in group 2. And group 3, they are the stars that don't present at the moment of the observation emission lines. If you remember what I said before, B stars present or have presented some moment emission. So the emission is not always observable in the stars. Sometimes you can observe emission and you observe later, and the emission is not anymore because the disk is not anymore. So they put their objects in the diagram made by Lenorsa with the same lines, and they found out that the group 1 stars are in this region in the diagram, and the group 2 are in a more wider region, not so close to the optically thick case. So these groups trace also the optical depth of the circumstellar envelope. Another work that I would like to mention is one by Granada and collaborators of 2010. They also observed a sample of BE star in the K and L band and made 2 different diagrams. One is the same that the nurses did with their stellar sample. Here is the group 1 stars, and this is the group 2. And another diagram that was based in some other that was done before, but with other lines, bracket alpha and bracket gamma, but it includes also includes also bracket gamma, bracket alpha Fun gamma and bracket gamma. And there is also a different sections for group 1 stars and group 2 stars. This is the optically thin case, and over there is the optically thick limit. And another interesting result from this work is that there is different values for the ratio between the equivalent width for bracket alpha, that is the one that is here. This is bracket alpha, this is bracket gamma, and this is bracket delta, the ratio to the equivalent width with bracket gamma. So it's all here, it's 1. So you can see here that for group 2 stars, the ratio between the equivalent width for bracket alpha over bracket gamma, it seems to be higher than 5 times, since for the group 2, the group 1, sorry, the ratios are smaller. So this works, as I mentioned, was based on observations made in the L band mostly, but also on the K band. And there are another works that focus in one specific line, or focus on one spectral range, or focus on one single object. So we wanted to obtain like a more complete picture of the properties of the circumstellar environment of these stars. So we wanted to collect near-infrared spectra in a wider spectral range with medium resolution, but for not just one object, but to a sample. So we observe with Gemini and with Las Campanas observatory using HDUST and fire a sample of 22 BE stars, galactic BE stars. And I am showing here some of the spectra that we obtained. This is the J band, H, K, and L. Previous work were focused mostly in these two bands. You can see here bracket alpha that I mentioned before, Fun Gamma, the Humphrey series. Here is the Fun series, so it's not very good in the upper part. Bracket series and Paschen beta. So you can see that there is a lot of hydrogen lines to observe in the infrared part of the spectrum. So the first thing we did was to classify these stars according to Meniken's criteria in group 1, 2, or 3, where there's no emission. And we measure the parameters of the lines that we observe. So we can see here in this picture, these are the relations that Granada proposed. This is the limit of 5 times for the ratio between the equivalent with bracket alpha over bracket gamma. And this is the 3 times for the same ratio. So the red symbols that I put here are those stars that if you see the spectra and you use Meniken's criteria, you put it in the group 1. And they show that this relation is over the line that Granada mentioned before. For the blue ones are those that are in group 2. If you see the L band, like for example here, they are the group 2 according to Meniken's criteria. And if you see the equivalent width of bracket alpha and bracket gamma, they are following this relation that Granada mentioned. But there are a group of stars that are here, the green ones, that if you see the L band spectra, you see that the Humphrey lines are not as intense as bracket alpha and Fun Gamma. So you will put it in the group 2. But this equivalent width ratio are more close to the values that we expect for group 1. So we start thinking that, well, this could be some kind of transition in stars, because the stars are not always present in the disk in the same conditions. So it could be possible that they are moving to one group to the other. So after that, we made the North-South diagram for our stellar sample. The colors and the symbols are the same for the previous figure. This is the North-South diagram with the optically thick and optically thin limits. And this is the other diagram that Granada was made. We see also the different limits, and we see the group 2, the blue symbols in one region, and the red and green in another. But what was the problem? Was these two diagrams use lines that are observed in the L and K band. And for us, observing the L band was more complex, because we observe with Gemini in the cross dispersion mode, and we obtain J, H, and K band together, and the L band in a different observation that took more time. Moreover, in fire, in Las Campanas, we can observe up to the K band. We cannot observe in the L band. So we had a subsample of our sample for which we didn't have L band observations. So we cannot use this Meniken criteria or put it in these diagrams. So we wanted to find other lines that if we made the diagrams similar to this, we can get some information about the envelopes. So we made these two diagrams that I'm showing here, that use lines in J, H, and K band, but not in the L band. So you can see the distribution is quite similar to the Lorentz diagram. There is the optically thick and optically thin limits, and the blue symbols are in the lower part, and the red and green symbols are in the upper part. So when we saw these plots, we say, well, the red and the green symbols looks that they are sharing always the same position in these diagrams. So we think that we can separate between group 1 and group 2 using quantitative criteria, but to this appearance of the Humphrey series and the L-band spectra. So if you put some limits in the dashed line, you can split the sample between group 1 that now contains the red ones and the green one symbols, and group 2 that are the blue. There is one object that is here, that is 105 Tauri, that if you see the Lorentz diagram, it's just in the limit that we put. So we think that, yes, this could be an object that is going between one group and another, but all the blues are group 2, and the red and green are group 1. So using this, we could classify these green ones. The green ones are those without L-band observations, so we couldn't classify it with Manningham's criteria, and we couldn't put it in these diagrams. So we can see that these ones seems to be more close to the blue ones, so we classify that as group 2. And there is one here that it's in the middle that remains unclassified. So for our stellar sample, we classified these ones. I won't mention all, but these stars in group 1, and these are over there in group 2. And we have 2 stars in group 3 that are those without emissions, so it's not in either of these figures, and one that is still unclassified because it's in the middle of all the plots. It is worth to highlight that for the group 1, the 9 stars that we put in group 1 have temperatures higher than 18,000, while 7 of the 10 stars in group 2 have temperatures below these values. One of these is the star that I mentioned that was just in the limit in the Lorentz diagram. And this difference in the temperatures agrees with previous results because it was mentioned by Sabgal that late BE stars present disks that are more tenuous and optically thin than early B-type stars. But as early type stars can develop optically thin disk when the optically thick disk that they could develop in some moment starts to dilute. So you can have both type of disk for early type B star, but only optically thin cases disk for late BE stars. So with these results, we define new complementary criteria up to the Manningham's classification to separate the BE stars according to their disk opacity. And some objects in our sample present optically thick envelopes, and another present extended and optically thin envelopes. So this was published in an article that is simultaneous JAK L-band spectroscopy observation of galactic BE stars. The part 1 involved this infrared atlas that I mentioned. So now we are working on characterizing the circumstellar envelopes more deep than just with these diagrams. We want to analyze each of these spectra and each of these envelopes. So one of the first things we did was these figures, when this dashed line is the radius for the bracket lines over one particular line for the optically thin case, and the continuous line is the ratio expected for an optically thick case. So you can see that the higher members of this bracket and also in the Humphrey series are close to the ratio expected for optically thin envelopes. And in some moment, the lines are like moving or are separating for this optical thin case to the optically thick. In which line this separation occurs is not the same in every envelope. And you can see here, for example, that for the Humphrey lines in this star, I didn't put which star it was, you have these three lines that doesn't have the ratio expected for an optically thin envelope, but in these objects, it seems like all the lines are in the optically thin case. So we think that this different kind of behavior may give us clues about the properties of the disk, about how the density change in the disk. But to perform a better analysis and to analyze this and to analyze the spectra, it is needed to have a synthetic spectra to confront them with the observations, and thus haven't been done before. So we started to analyze and to model to obtain a synthetic spectra. For that, we choose to use the HDUST code that has been used previously mostly to model H-alpha or the spectral energy distribution for BE star, but not to model infrared lines. So the HDUST code use a 3D non-LTE Monte Carlo code that allows us to solve radiative transfer, radiative equilibrium, and statistical equilibrium in a 3D geometry. You can put different gas distribution, different gas density distribution, and different velocity distribution for the disk. And it uses hydrogen atom with 25 levels. The first 12 are in non-local thermodynamic equilibrium, and the other 13 are in equilibrium. And the density that we use follows this relationship. When in the radial direction, it's a power law with a central density rho 0 and an exponent n. And in the vertical direction, it's a Gaussian with this scale height that it's the one that corresponds to a isothermical vertical disk. It was some previous work by Vieira and collaborators for 2017 that analyzing the spectral energy distribution and fitting densities and the exponent of this density law, they found that the exponent is related with the dynamical state of the disk. So they found that for n values higher than 3.5, the disk is forming. For n values between 3 and 3.5, the disk is like in a steady state. And for values below 3, the disk is dissipating. They also found that there is a forbidden zone, so we cannot have disk with a small n and high density. This ends and a smaller n value means that the density falls very slowly. And if you have a higher n value, the density falls very quick. So using that, we made some models using values in this square. Values for n, 2.5 and 4, and densities with the logarithm between minus 12 and minus 10. We use just one central object for now. We are just starting with this. So we choose to use mass for our central star of 10 solar masses, polar radius of 5.5 solar radius, luminosity of 7,500. That give us a star with a temperature of around 24,000. And these values for the ratio between the rotational velocity and the orbital velocity of 0.7, that give us a rotational velocity of 370 kilometers per second. And we use this value for the limb darkening. So we made different models with different parameters for the density law. This is the different values that we use for the central density and for the exponent. And you can see here that the radius that we choose for the disk is not the same for all the models. This is because we search for the radius that where all the lines are completely emitted. I mean, if we put a small radius, you may lose part of the emission because of this line. This line could be emitted further on the disk. So we made different models, changing the radius, and found where we can be sure that more than the 95% of the emission is reached. And here is one example of one of the spectra for these parameters for the disk. You can see bracket alpha, bracket gamma, bracket alpha, beta, gamma, delta, and so on. It is worth mentioning that this is not like an actual spectra of the stars. You just model these lines, because if you observe the spectra of the stars, you should have here the Humphrey series, but we are not putting the Humphrey series in our modeling for now, because we can go just up to transitions with an upper level of 12, because we are using an hydrogen model that models the 12 first level in a non-LTE. So we cannot model for now more than these transitions. So here are some line profiles for these n values, and each color is different densities. So you can see that, well, this is for an inclination 0, that is polon. So you can see one peak for each line profile. And you see that the intensity is not the same for every model. So this is better to look if we see something like that. Here, we measure the equivalent width of all the lines, and we made the ratio between each equivalent width over the equivalent width of bracket 12. So this is 1 for bracket 12, and for other lines that have an equivalent width higher, this is the different radius. Each panel is for one different density, and each color is for different n values. So for example, for the smaller n value, it's this violet that we can only combine with the lower density. There is a strong intensification for the lines going from bracket 12 to bracket alpha for all the inclination, but they are more intense for lower inclinations. In the case of n 3.0, that is the orange lines, the height is also increasing from bracket 12 to bracket alpha, but the slope is different for each density. You can see that here the increase is so much steeper than here. And for lower inclinations, the increase is also higher than for the lowest inclination that we use, that it's 60 degrees. For 3.5, the behavior is similar. The slope of the increase is also steeper for the lowest densities. This is the green ones. And even though the higher order lines are more intense for the highest densities, since then the slope is different for the first members, we finally obtain intensities that are quite similar. And finally, for the higher M value that we used, that was 4, that is the red lines, the densities are the smallest that we obtain, and the increase is not so different for each density. We made also this diagram with the flux ratio, not the equivalent width, also over the flux for bracket 12. And it's also different color for different N values and different panels for different densities. And we can see here that we have non-monotonic behavior, that if you remember the figures with the data of our large sample, we have non-monotonic behavior in these curves. And the lowest curve is for the highest N value. And for the lowest density, this maximum of these curves depends on the N value. I mean, for smaller N value, this maximum is higher than for higher values of N. We also made this other diagram with the equivalent width for bracket alpha and bracket gamma. So we can see the same relations that I showed you before, the ones proposed by Granada. And we see that the models with a higher M value present a smaller values for the equivalent width and are close to the values that we expect for group 1 objects. For the group 2 position, that it should be inside these triangles, it seems there are only objects with the smaller density that we have. And we made also these plots with the equivalent width of the bracket 11 and bracket 12. And it seems to be close to this line that is the expected ratio for case B recombinations, I mean, in the optically thin case. And for a fixed M value, that it's different colors, the higher the density, I mean, the higher the symbol, the higher the values of the equivalent width. So in our sample, we had 2 objects that have parameters that are close to the parameters that we use for our synthetic model. So we compare our measures for the bracket lines with our models. So this is the 4 bracket lines that we observe in this object, and we compare it with the simulations. The dashed line is the spectra of MX puppies, and the continuous gray line is the best fitting model that we found. There are some differences in the wings that could indicate that the non-coherent scattering is significant in this object. But this is also possible that a single power law, it's not enough to fit and to describe the complexity of the circumstellar envelopes of these objects. So we choose as a best fitting model a compromise solution between these different things that we found. So this is the parameters that we found for this best fitting model. And according to these N values, this disk should be in a stable or starting to dissipating. We also see how our measures fall in this these other plots that I showed you before. So this is the n value that we found from the spectra, and this is the density that we found. And our data, there are these black stars, seems to agree with the curves that corresponds to the values that we found from the spectra. But here in this, for the given width of bracket 11 and bracket 12, our object fall little far from the models, but this could be related with the difference in the wings because of the poor fitting in that part. The other object that we had was the Aquari, and this is the best fitting model that we found for the same lines that I showed you before. And this is the parameters that we found, n value 3.5, that put these objects in a forming or stable disk stage. And for these diagrams, we found that it's not a very good agreement in this part, but yes, in this one. So it could be possible that there is some problem with the normalization of the spectra or something like that, that could affect that, but the spectral fitting is quite good. And here, the position of our star also falls in a region that it's in a good agreement with the parameters that we found with the spectral fitting. So this, up to this, it has been published in the Galaxies special issue that was published a few months ago. And this is what we are doing now. As I mentioned before, we obtain the models with different radius up to see that all the emission is included. But we saw that according to the density or to the n exponent or to the 9, this complete emission was reached in different radius. So we wanted to see what happened if we put different ratio. I mean, what could we see if we are seeing a truncated disk? So for example, here, there is, if you see if we model with different radius, the blue ones are for 10 stellar radius, the orange for 20, and the green for 30, you can see that the higher member of the series, it looks the same no matter what radius you put. But if you see the first member of the series, it is starting to be different. For example, for bracket alpha, if we model just up to 10 stellar radii, we are not seeing the complete emission that this line could be. So we need to, I mean, a complete disk emitting bracket alpha should be bigger. But for another, this was for N4, and this is for N3.5, so the density is falling slower than here. The difference is significant even for the higher member of the series. Of course, for bracket alpha, it's more significant, but you can see difference between the models with different radius for all the lines. So here I show the flux for these lines relative to the flux with the maximum radius that we put for each model. This line corresponds to a different n value, each line of these different subplots, and each column is for different density values. Each color is for different sizes that we put in the model. So we can see that for the first members of the series, bracket alpha, bracket beta, and bracket gamma, the difference between different radius between modeling with 10 or with 30 or 40 is significant for most of the models. But for the higher order members, this difference is only significant when we have a high density, like here, for example, or a smaller value for the n exponent. If we see here, this is the diagram with the flux over the flux in bracket 12, and it's again one line for one n value for 3.5, 3, and 2.5, and one column for each density. And you can see here also that the difference between different radius are more significant only if we are observing higher disk with higher density values, or with smaller n values, like here. It's like in this part of the subplots. Here, there is no difference between different models. And in this case, when there is difference, the decrease of the flux is steeper for the smaller radius. So it means that we are losing a lot of the emission for this, the first members of this series. So we saw that the increment of the intensity through the series depends on the rho, the density, and the n values, the exponent. And the lines usually increase from bracket 12 to bracket gamma with a slope that depends on the density value. We also see that the behavior of the equivalent width of bracket alpha and bracket gamma lies like in different position according to the central density. And for the equivalent width of bracket 12 and bracket 11, the model follows a linear relationship that is close to the expected for the optically thin case. And regarding the truncation effect, it seems that stable and dissipating disks are the most affected by truncation, because the density is significant up to regions that are not so close to the stars, so the density is falling very slowly, especially for those with higher central densities. But for forming disk, for disk with an n value that is higher, the truncation effect is important only if you're observing disk with a high central density. Otherwise, the density falls very high, and it's the same to model that is with 10 stellar radius, or for 20, for example. So with what we want to do next, as I mentioned before, the model that we are using includes an hydrogen with 12 levels with non-LTE. So we want to include more lines because in our observations, we are going up to bracket 20 or more. And we are observing, for example, lines of the Humphrey series that with a 12 level atom we cannot model, because we need upper levels that are higher than 12. So we need to include more lines. We need to include more levels for the hydrogen atom. In the last weeks, we made some steps forward these directions. So we are very happy about it, but it's just some very, very recent results. So we are working on that. We are working also on including other hydrogen series, because this will give us like a more complete picture. In the case that a simple power law is not enough, we can see how different positions, different parts of the disk are modeled with different n values, looking for different hydrogen series, because they are forming in different regions in the disk. And we want also to add other spectral types, so we can compare with another stars of our sample, so we can model all our spectra and to compare and obtain parameters for the disk of this stellar sample. So that's all for now. So thank you for your attention. And if you have any question or suggestion or comment, I'm all ears.
All right, thank you very much, Dr. Cochetti. I'll applaud on behalf of everyone. I'm guessing there might be
Thank
some
you.
reactions on Zoom. Okay, so we have time for questions. And actually, in the chat, we already have a question comment. So Alex Carciofi,
Hi, Alex.
right, writes that he thanks you for the excellent talk and congratulations on the paper. However, it seems that he had to leave, so he just wanted to comment that in HDUST, the number of NLT and LT lines are free parameters that you could change to better
Yes, I
model
am
the lines.
trying to
So I guess
change
that's
that, but it had some problems with that.
exactly. So it sounds like you already pretty much addressed this.
Yeah.
Okay, so I'll open it up to other questions. Does anyone have questions for Dr. Cochetti? So it can be in the chat, or you could unmute yourself and ask you the question.
Well, I'll ask a quick question. This is Rico Ignis. Nice talk. Pi Aquaria is a gamma CAS analog. Do you have any tweaks to the model input or the situation when you have a gamma CAS object?
Do you mean like a BE or just about gamma gas? I think that I don't have that particular object in my sample,
But
but
Pi
I'm not
Aquaria
sure
is
about your
gamma CAS
question.
analog, I think.
But it's a PE. I don't remember now if gamma gas have some particular
But I think they're
characteristic.
hard X-ray sources and things. Does that include, I mean, hydrogen is completely ionized and stuff, but, can it alter some temperature situation?
No. We're just working for now with regular BE stars.
Okay.
Yeah.
Thanks.
You're welcome.
Okay, are there any other questions? Oh, I see that there's something in the chat, so I'll just read it out for everyone. John Bart saying, nice work. Most of the stars you showed are pretty bright and well observed. So is it worthwhile to use, for instance, the big database on BESS to place your infrared spectra into context? That is, H-alpha time series can tell you if a disk is growing versus steady versus dissipating.
Yes, for some of our objects, we have actually more than one, just one spectra. And in my PhD thesis, we work with this spectra and like following the objects, and we made some comparison with what we observe in H-alpha, and we use the database. Yes, it's fine and very nice work, just trying to solve the puzzle of what we observe in the infrared and what we observe in bracket alpha, in H-alpha. Yes.
Okay, other questions for Dr. Cochetti? So I guess maybe piggybacking off of John's question, I might just ask also if you've had any look at, for instance, optical photometry and those sorts of things too.
No, photometry, no. I'm more focused on spectroscopy, but we have obtained also optical spectroscopy. Not for this object, I think, because they are northern objects, and we are used to observe with the optical with the telescope here in Argentina. But there are some that we have the complete picture, but yes, it's our final goal to obtain a more complete picture. It's a hard puzzle.
Great, thanks. Okay, are there any more questions? All right, so I want to thank you, Dr. Cochetti, once again for a very nice talk. I think this was quite appreciated. And I'll also thank everyone who attended today. So, of course, we'll have our next seminar next month, and the details will be sent to you shortly. So stay posted for that. So have a great month, everyone, and we'll see you again soon. Thanks again, Dr. Cochetti.
Thank you, and thank you for coming.